All right, folks, we have done it. We have successfully predicted spontaneous changes and kicked some supernatural thermodynamic butt along the way. But let's take another look at the meaning of spontaneity, and that is with the understanding of product-favored reactions and reactant-favored reactions. So for both scenarios, we're going to be looking at situations where the reaction is going to proceed spontaneously until it reaches equilibrium. At the point it reaches equilibrium, the reaction is considered non-spontaneous. So for us, green is going to equal spontaneous. So we see a green arrow here, that's spontaneous. We see another one here, green arrow, green arrow. That represents spontaneity. Red is going to represent non-spontaneous. So we have a red arrow here, here, and here. Those are all going to be considered non-spontaneous. On the y-axis for these graphs, we're going to have the free energy or delta G of the system. And on the x-axis, we have the extent of the reaction. So we're going from left to right. For this overall product favor reaction, we're using A and equilibrium to form B. So we're going to go from A forming B. And this overall reactant favor reaction, we're going to be C and equilibrium to form D. So we're going from C, which is our reactant, to form D. Let's focus on product favored reactions first. So product favored reaction just means that the reaction is where the equilibrium constant is greater than 1. So what is the equilibrium constant? If I have an expression that's A and equilibrium for B, my equilibrium expression is going to be the concentration of B divided by the concentration of A. And I'm saying that this value is going to be greater than 1 because this is going to favor the product. That means our concentration of B is going to be a larger amount than our concentration of A. So our reaction is going to start off with A, and then as we continue on with the reaction, we're supposed to end with B once we reach our equilibrium, right? So the reaction is going to start spontaneously, as we can see in green, all the way until we get to equilibrium. Here at equilibrium, it's going to stop. And so after this equilibrium point, you're going to need energy in order to continue on. That means the red arrow means that we are dealing with something that's non-spontaneous. So for a product favored reaction, our delta G is going to be less than 0, and our K value is going to be greater than 1. And this graph also shows that if we want to go into the reverse reaction from B to A, we're going to need a lot of input of energy because this is a non-spontaneous process. As you can see, it's a red arrow if we want to go from B to A. But from A to B, it is spontaneous. For a reactant favored reaction, we're going to start with the expression C and equilibrium to form D. So we're going to start off with our reactant, and as we go along, we're going to, of course, produce our product D, all the way until we reach equilibrium. Now our K expression is going to be the concentration of D divided by the concentration of C, which is going to be less than 1. That means that we have way more reactants than we have products. Let's see if we can visualize that on our graph. So as you can see, we are starting off with our overall amount for our reactant C, and we're going to go all the way into equilibrium. This portion of this is going to be spontaneous. Once you reach equilibrium, though, you're going to need to have an input of energy here because our delta G value is greater than 0. And if it's going to be greater than 0, it's considered non-spontaneous, which is why we have a red arrow going up. So of course, we focus on when the reaction is going to be spontaneous and then when it stops at equilibrium. So when we're at that point, we are still going to be dealing with mostly reactant, which is why our K value is less than 1. And if our K value is less than 1, that means our delta G value is going to be greater than 0 or non-spontaneous. So in summary, we can think of the term spontaneous as referring to the part of the reaction where the free energy decreases. It's going to continue to decrease until we reach equilibrium. And a product favored reaction is going to predominantly move towards the products, while a reactant favored reaction is going to show relatively little tendency towards the products itself. We can even go further and use the previous table that shows the relationship between delta G naught and K, which is our equilibrium constant, and we can go ahead and use that to help us verify the information we see. Again, when delta G is positive, our K is going to be less than 1 for a reactant favored process. And that's true because as you can see here, we are increasing towards the reverse reaction. The reverse reaction means we're going towards the left or towards the reactants themselves, which verifies our reactant favored reaction here. We can do the same thing with the product favored reaction. Our delta G value is going to be less than 0 or smaller. So when we get to a small delta G value, we have a K value that's greater than 1. Now, if we have a K value that's greater than 1 and a delta G value that's less than 0, we are going towards the product. And so it makes sense that we would have a product favored reaction. All right, folks, we have fought hard with Sam and Dean learning about spontaneous change. Make sure to spend time reviewing the information and layering the best you can. There is a lot of conceptual information and calculations So take your time to organize yourselves and get help when you need. As a bonus, let's see Sam and Dean fight against more supernatural thermodynamic threats when they save a family from a demonic presence. See you there, folks.